Let's talk about multi-factor designs. In a multi-factor design, we have more than one variable. The number of variables or factors can be significant, or we could possibly have significant interactions. We can also have situations where we have more factors than we can afford to analyze. This necessitates the need for fractional factorial designs. When doing factorial designs, technology is going to be essential. Minitab is considered to be the premier resource for design of experiments. These designs will build upon the design plan and trade-off table discussed in Module 2. Let's consider this design. Suppose we have a 2x2. Each factor has 2 levels. This would mean 4 experiments. To further improve the robustness of this design, we will add 3 replicates. In other words, we will run the experiment for each configuration 3 times. Now some context. Suppose we are investigating the conductivity of nitinol wire. Nitinol is a memory metal and can assume any number of preformed shapes based on processing conditions. Our 2 factors are temperature and nickel content. Our response variable will be the elastic modulus. The data table is shown here. Note that the minus means a low level and a plus means a high level. We will assume that alpha is 0.05. We use technology to run this as a full factorial design with 3 replicates. This design is very manageable. Let's take a look at the output. First, the ANOVA shows that temperature is a significant main effect. The p-value is 0.002, which is much less than 0.05. The nickel content and the interaction between temperature and nickel content are not significant because of the sizes of the p-values. We also notice that the error sum of squares is larger than the sum of squares of these 2 factors. This suggests that there might be a factor influencing elastic modulus that we have not accounted for. The regression equation is found at the bottom. Notice that this is a multiple regression with each main factor and the interaction term. The model summary shows an R-squared of 75.58%. This means that the regression equation accounts for 75.58% of the variability. Here is the second half of the analysis. As you can see, the previous results are affirmed. The Pareto chart shows that temperature, A, is the largest effect, followed by nickel content and the interaction. Now let's consider this example. We have a 3-factor design with 2 levels and 1 replicate. Here, the response variable is resistance. Humidity, cure time, and percent EPDM are the factors. We will assume that alpha is 0.05. Like before, we run the analysis using an appropriate software. Some of the results are shown here. On the left, we have the ANOVA table. Notice that humidity and percent EPDM are statistically significant at p-values of 0.022 and 0.007 respectively. We also see that the interaction between humidity and percent EPDM is also statistically significant at 0.014. The model summary on the right shows an R-squared of 99.99%. This means that 99.99% of the variability in the process can be explained by the model. This is very good. The regression equation is also shown. It should be noted that all 3-way interactions have been ignored as they are likely to be insignificant. Here we have the Pareto chart indicating the substantial effects. Percent EPDM has the largest significant effect, followed by the interaction between humidity and percent EPDM, and finally humidity. We can also see the same result on the right in the coded coefficient table. When there are many factors and limited resources, a fractional factorial design can be utilized to obtain representation of each factor, but with far fewer trials. There are trade-offs with this approach. As the number of confounded variables increases, we add new factors and increase the reduction factor. Consider an experiment where we have 6 factors. Were this a full factorial experiment, we would require 2 to the 6th or 64 runs. Economically, this is quite prohibitive, especially if our experiments are destructive. We have decided to look into a fractional factorial design. With 2 reduced factors and 6 factors total, this gives us a resolution 4 design with 16 runs. In this example, we are investigating a powder paint process. Our factors are temperature, thickness, bond, feed rate, catalyst, and conductivity. Hardness is the response. Again, there are 2 levels for each factor. The 16 runs are detailed here with the response. Assume alpha is 0.1. Technology is used to generate our results. First, note that we have an alias structure to consider. Since 2 of the factors are defined by the 2 generators on the trade-off table, we see that there is substantial confounding. The aliases are shown on the left. Note that the defining relationship is given first under aliases. Also note that there are 4 aliases for the identity. This is exactly what we should have since there are 2 reduced factors. At the top, terms that are totally confounded are identified and summarily removed. Note that all interactions higher than 2 factors have also been removed. Below we have the regression equation based on our analysis. Let's look at the ANOVA. We see that temperature, thickness, and the interaction between temperature and thickness are significant, with p-values of 0.071, 0.013, and 0.095, respectively. Recognize that the interaction term between temperature and thickness is confounded with the interaction between bond and catalyst. This means that we cannot distinguish the effect between these 2 interaction terms. The model summary shows that this model is capable of explaining 98.02% of the variability. Also note that the adjusted R-squared is lower than the R-squared. Adjusted R-squared will decrease when a variable improves the model by less than what is expected by chance. This is the case here and should be expected given the number of factors under consideration. The coded effects table aligns with the ANOVA table. The thickness has the strongest effect, followed by temperature, and then by the interaction between temperature and thickness, added to the interaction between bond and catalyst. The Pareto chart aligns with the result from the previous slide. You will notice that the contribution of the interaction between bond and catalyst is so small it does not appear. Nevertheless, this still does not allow us to dismiss this interaction.